Good morning, friends. Welcome back to my YouTube channel Medical Classes by Dr. Srinidhi Kumar Acharya. Don't forget to subscribe my channel and also please give your valuable comments. Friends, as you know, we are discussing about the basics of genetics, especially single gene disorders. And in the last few classes, we have already discussed about the basics of genetics, dominant disorders, and also recessive disorders. Now, today we will going to discuss about X-linked disorders. Okay, X-linked disorders. X-linked disorders means it is only related to 6 chromosomes. We are not talking about autosomes. We have already seen autosomal dominant, autosomal recessive. We have already seen. Now onwards, we will see X-linked dominant and X-linked recessive disorders. So there is a male and female difference is there because sex-linked chromosomes or sex chromosomes in male is X and Y, and sex-linked chromosomes in the female is X and X. And that makes the difference as far as the male and female ratio is concerned. In autosomes, we don't have any such problems because autosomes are equal for male and female. But X chromosomes, the sex chromosomes are not equal for male and female. That's the difference. So there is some trickiness is there in this aspect, number one. Okay, so we'll look into it. Now, similar to autosomal dominant disorders, and there will be also sex-linked dominant disorders and also sex-linked recessive disorders. Okay, among the sex-linked disorders, there are two types of disorders because sex-linked disorders means one X is there in female and XY is there, isn't it? So basically two important chromosomes are there. One is X, another one is Y. So we have got X-linked dominant and X-linked recessive, Y-linked dominant and Y-linked recessive. These disorders are there. So we have to, among the sex-linked disorders, there is X-linked and Y-linked disorders. Okay, now first we will see the sex-linked disorders. The sex-linked disorders are either related to X or Y, as we know. But sex-linked disorders are also called as X-linked disorders. Why? Why? Because if you see male, there is one X and one Y. One X is there. If you take the female, there is two X are there. So totally, if you see the 3X, majority is 3X, isn't it? So therefore, X-linked disorders are majorly, sex-linked disorders are majorly X-linked disorders. So another name for the sex-linked disorder is X-linked disorders. And Y has been neglected. Do you think so? No, it is not like that. Y is not mentioned here because Y-linked disorders are either maybe dominant or recessive. Dominant or recessive. Okay. So, but actually Y-linked disorders are very less. Y-linked disorders are very less. Y-linked related disorders may be dominant or recessive, both are less. Why? The reason is Y is basically a very small chromosome and it actually contains very few genes. Okay, there is only few genes are there, so chance of getting a disease is actually less. Therefore, the Y has been not given much importance there. Sex-linked disorders are also called as X-linked disorders. Okay, now Y will be only given to the boys and Y is not given to the girls also. So if at all there is a problem, only the boys will going to suffer, isn't it? Y is never given to girl. So if at all Y-linked problems are there, definitely it will be seen only in the boys because Y is only taken by the boys. Okay, so such disorders are very common. One of the common Y-linked dominant disorders, if you want to see, hairy pinna, you might have been observed in many people. There is a hairy pinna is there. Actually, this is one of the, not disorder, this is one of the Y-linked dominant inheritance. The grandfather is also having hairy pinna, father is also having hairy pinna, now the male child is also having hairy pinna. So this is possible. Okay, hairy pinna. So hence X-linked disorders are also called as sex-linked disorders are also called as X-linked disorders. And it may be dominant or it may be recessive. Now, so we will look into X-linked recessive disorders. X-linked recessive disorders are very common because most of the recessive genes will manage the enzymatic function, reaction and pathways. This is also same for the autosomes. In the autosomes also, the recessive genes are mainly related with the enzymatic function, reactions, pathways, intracellular enzymes, etc. That is the function of recessive genes. Okay, so if I say X-linked recessive, if only one X is mutant, then another X is normal. So there is no disease. So in case of female child, usually we have got two X. If at all one is mutant, another X will going to do the work and there is no disease. This is what actually we think. But actually it is not like that. Why? Because female has got two X, isn't it? But among these two normal X, one of the X will be inactivated in the very early part of the fetal development itself. Immediately after formation of the zygote, after 3 or 4 or 5 divisions, in the embryonic period itself, one of the X is inactivated and only one X is actually working. Okay, this is the interesting phenomenon. This is called as Marie-Lyon hypothesis. Okay, this is also called as Marie-Lyon hypothesis, where she says that, she proves that although female is contained in 2X, actually one X is completely working, another X is only partially working. It is not mutant, it is inactivated forcefully. Another X will go into, the stronger one going to inactivate the another X forcefully. So it is partially inactivated. It is partially inactivated. So she can inactivate the normal X or mutant. Sometimes unfortunately what happens during the time of this inactivation, sometimes a mutant X, if it is present, that may sometimes inactivate the normal X. Now normal X is working only up to 20% or 30% partially inactivated, and this mutant X is working to 100%. The mutant X will definitely cause the problem also, we know that, because another X is absent, that means almost all it is partially inactivated, and another X is only has to work, but it is mutant. So possibility of the disease is also there. So she can inactivate the normal and keep the active. So anything can happen. Normal has been inactivated or abnormal would have been kept active. Both is possible. Anyway, if one X is mutant, he runs a carrier state. This is the normal rule. X is there. We presume that, although this is a possibility as per Marie-Lyon hypothesis, for example, we now will assume that female means both X are there, both are active. Okay, for our understanding purpose, we take that. So if one is carrier, there is no disease. Most of the time, the female inactivate the X randomly. Okay, so a male cannot transmit X-linked disorders to the son. This is another important thing. Now come to the males. In case of male is always receiving Y from the father, isn't it? Male never receives any X from the father. To the male, X is always given from the mother. Father can give to a fetus, father can give X or Y both. If the father is giving the X, it becomes a female. If father is giving the Y, he becomes a male. So father cannot transmit any X-linked disorders to son, because he always give X to the female babies only. So X-linked disorders of the father, will be always transmitted to daughter only. Always transmitted to daughter only. So if the X of the male is mutated, and that will be inherited to the female baby or daughter only. So whereas if female contain XX, we know that yes, female mother contains XX, and if both are mutated, then what happens? She gives one mutated gene to daughter and another mutated gene to son. If the female contains XX and if it is one of the X is mutated, then it may be given to either male or it can be given either female. It may be given to either female. Now this is the possibility. We are talking about X-linked recessive pattern. Okay, she is a normal male here. This is a carrier female. The rules are same. 50% males and 50% females. Is it followed here? No. That rule is not followed here. Look at carefully. Normal female and carrier female. Now this is a possibility. She is XX, she is a carrier. Okay, these two are normal babies. Okay, XY, he is also carrier. He is also carrier. This is a male XY, but actually he is carrier. But although he is carrier, he developed the disease because X is one of the X is mutant, isn't it? There is no another X here. Here, female, she is a carrier. One X is mutant, but fortunately another X is there. Another X will go to do the work, so she remains carrier. But although male looks like carrier, as he is not having another X there, he is having Y instead of X. So there is a development of the disease. So this, although this is a recessive pattern, as there is no another X, this is just like a dominant pattern only. Okay, the mutant X is there, definitely it develops the disease. Now what happens next? Here the carrier female is there. She is married to the carrier. She is married to the normal male. She is married to the normal male. Now what is the possibility? This is X-linked recessive pattern. Okay. Now what is the possibility? There is a mother, there is a female daughter who is carrier. There is a daughter who is normal. There is a male who is normal, and there is a male who is carrier. But unfortunately, this is carrier. Although this is carrier, he developed the disease because there is only one X. There is no second X. Instead of that, Y is there. So he becomes diseased. So he is a diseased male. Okay. You look at here. A diseased male marries with a normal female. Diseased male marries with a normal female. Now diseased male, what is the possibility here? This is a female, she become carrier. Okay, this is also a female, she becomes a carrier. Okay, so this is XY normal, and this is this and this XY normal. What you observed here? Male is diseased. A diseased male always gives the X to any male, he gives the X to only daughter, not to the males. See, therefore males are not affected. Both the males are normal because female is normal, mother is normal, father is no diseased. As father gives X to only females, both the females are get carrier here. Okay, and both the males are normal. So this is another rule. Male always give a recessive mutant gene of X to daughter only. That is obviously known, and that's the reason. So in this case, the males are more affected. Where? When the mother is having carrier gene and she is married to the normal father, then what happens? Males are more affected. When father is get affected and father is diseased, he is married to a normal female, males are not much affected, females are more affected. This is important rule as far as X-linked recessive conditions are concerned. Okay, now this is what I already explained. Now you come into another situation where carrier female with a normal male. This is what we have seen. This is a carrier female. She marries to the normal male. Okay, so what we have so far seen here is diseased male with a normal female, but here carrier female. So what we have seen here, carrier female with a normal male, carrier female with a normal male, almost all same. Okay, so males are affected more. This part we have already seen. Now diseased male marries with a carrier female. This is also we have seen. Now females are more sufferers when affected male marries the carrier female. Now this is another situation. Male is totally affected and female is carrier. Okay, see here what we have seen, female is carrier, male is normal, and here what we have seen is female is diseased, male is diseased, female is normal. Here what we have seen, carrier is female and male is normal, but this situation is different. Female is a carrier and male is deceased. Now what happens? See, female is carrier, male is deceased. Now, if you look into the possibilities, okay, so what happens? X and X comes together, both are mutant, so she is a female. X and S both are mutant, she is deceased. This X and this X comes over here, this is a carrier, female carrier. This Y and this X comes, X and Y, this is affected because he is a male, affected, and this is not. So this is a possibility when a interfamilial marriage happens and a affected male or deceased male marry with a carrier female. What happens? One will be normal. Okay, one male will be affected. That means one male will be deceased. One female will be deceased. One female will be also deceased, and one female will be carrier. Okay, one female will be carrier. So what you can see here, females are more sufferers when affected male marries with a carrier female. Okay, if you look at this, females are more affected. Otherwise, X-linked recessive disorders, females are rarely affected because they've got two X, isn't it? If the one of the X is affected also, carrier also, another X is there, so that will do the function. But when this situation comes, affected male marries with a carrier female, female is also get affected. So usually the females are not affected in the X-linked recessive disorders. But when a carrier female married with an affected male, the disease can manifest even in case of a female baby. So in some conditions, female inactivate the healthy X and keep the affected X chromosome more active. This we have already discussed. Usually they have 50% chance of inactivating either the paternal X or maternal X. This is also we have discussed. Suppose female has one X chromosome which is mutant. By chance, if it is inactivated and 70% of the healthy X is active and kept 70% of the mutant X active. Okay, so one situation is, suppose a female has two chromosomes, X chromosomes. Among them, one X chromosome is mutant, and that mutant X chromosome is inactivated. It is well and good, no problem. But sometimes what happens, the normal X will be inactivated and the mutant X will be kept active. Then she may develop some of the manifestations, not a disease actually, but she may develop some manifestations, because when I say inactivated, it is not complete inactivation. Normal is inactivated means it is only 70% inactivation, 30% it is active, so it is still producing something, some of the genes and all, proteins and all, but she may develop some of the manifestations. So this is in X-linked chromosome. Although female is safe, because of this particular problem, female may develop some of the problems. The same has been explained in this picture. Now come to the last one, X-linked dominant conditions. X-linked recessive is okay, X-linked dominant conditions. Now, classical example of X-linked dominant condition is a hypophosphatemia recurs. Dominant means one, if in the X chromosome also there is a recessive genes, there is also dominant genes. So far we have talked about the recessive genes. Now talk about the dominant genes. The rule of dominant is, if one X or one gene is affected, definitely there will be a disease. Isn't it? Look at this example. This is actually hypophosphatemia recurs, is one of the X-linked dominant condition. X-linked dominant condition. Okay, so here male is deceased because one X is mutant. If one X is mutant, it's a disease in dominancy. Female is also one X mutant, that's a disease because it's a dominant. Now when they made together, they have got four kids. Here two of them are diseased, again one male and one female, and one will be one will be carrier and one will be normal. Now the question is, in the dominance there is no question of carrier, isn't it? We know that in the dominance, see, these two are completely diseased, no doubt. Why these two? Because both X are involved here. Why this one? There is only one X which is involved here, that means mutant here. Here both the X are mutant. In case of female, definitely there is a disease, severe disease. If one X is also involved, there will be disease because it's a dominant trait. But here it is both are involved, therefore penetrance is very high and there's a severe disease. Okay, this male, he has got only one X and that is mutant and therefore he is deceased. Okay, now what about this female? As this is a dominant trait, so she is also having the disease. Okay, but penetrance may be low, manifestations may be less because in autosomal dominant, in the autosomal dominant we have seen there are many this pleometry and all this many things, low penetrance, many things are there. So she may be having low penetrance, but she is deceased, and one will be normal. Who is normal? Y. That means male will be one of the male will be normal because this is what happens when a diseased male married with the diseased female. Why this male will be normal? The male will be normal because father transmit only Y to the son. He is not giving X to the son. So he is giving X only to daughter. Therefore, daughter is deceased. Both the daughters are deceased, but one of the male is normal. So that's the reason in case of hyperpositivity case, more females are affected and less males are affected. In X-linked recessive, more males are affected, less females are affected. But in X-linked dominant, less males are affected or no males are affected and more females are affected. That's the difference. Okay, so X-linked dominant and mutant in female and the male is normal. This part we have already seen. Now we have got another inheritance that is called as mitochondrial inheritance. This is probably the last one in the single gene disorders. Okay, now some of the inheritary factors are also there in mitochondria, and it is believed that not only in the chromosomes, inside the mitochondria also there are some genetic factors which are going to inherit. Okay, such inheritance is called as mitochondrial inheritance. We know that in the chromosome there is genes and that will go into inherits when there is formation of zygote. But even the mitochondria also contain some of the genes which are inheritable and that is also transmitted. And such type of transmission is called as a mitochondrial inheritance. Now the question is, in the ovum, there is mitochondria, isn't it? And because ovum is not moving anywhere, only sperm is coming there, and ovum will be there in the ampulla only. So it contains the mitochondria, it contains the cytoplasm, everything, and sperm enters there, and there is the formation of zygote. Now what happens with the sperm is, sperm has to move in the genital tract. For that, energy is required. So what happened? All the mitochondria of sperm, so that will be modified into acrosomes, a cap-like structure, and that is the one which gives the energy or power for the movement of the sperm to the site of ovum in the female genital tract. Okay, by the time sperm reaches the ovum, what are all the mitochondria which is present? So that has been totally utilized for the purpose of the energy, and only the nucleus portion of the sperm will go inside and mate with the ovum, and there is formation of zygote. So what you understood is, there is no question of transmission of mitochondrial inheritance from the father to the offspring, because father's mitochondria, that is sperm's mitochondria, has been already utilized and degenerated by the time it reaches the ovum. But ovum's mitochondria, it is intact. So in case of mitochondrial inheritance, always and always, it is mother who is transmitting this to the kids. Okay, mother, irrespective of male and female. Okay, if that particular inheritance is there, it is from the mother side only. That means if the mother is having this particular mitochondrial inheritance problem, some of the genes which is present in the mitochondria, if they are mutant, then what happens? All the children are get affected because mother give 1x to the male and 1x to the female. For the male also mother gives the x, for the female also mother gives the x. Okay, so this is what is called as mitochondrial inheritance. This is a picture. If this is mother having mitochondrial inheritance mutant gene, this father, he is normal. Now see, all the kids are affected because it's only transmitted by mother, because mitochondria is only present in the ovum. Okay, at the time of the zygote, mitochondria is only present in the ovum. In the sperm, it is not at all present. There is no question of transmission from the father side. This is called as mitochondrial inheritance. So thus we have completed three important things. One is dominant disorders, recessive disorders, and mitochondrial inheritance. And these are the three important things which we consider under the Mendelian's genetic disorders, Mendelian type of genetic disorders. Okay, so with this we completed the basic information of genetic disorders, especially single gene disorders. Okay, thank you very much, and we will meet again, and some other day we will take the extended classes of this genetics. There are many things are there in the genetics, very interesting also. Once you understand these basics, then the genetics is very interesting. Otherwise sometimes it may be a confusing factor. Okay, so anyway, thank you very much for being with me, and meet again. Please don't forget to subscribe my channel, and also please give your valuable comments. Thank you very much.